Hi, my name is Brian Heckman. Thank you for watching my paper presentation for CS6263, Introduction to Cyber-Physical Systems Security. For my presentation, the paper that I chose is titled Differentially Private Password Frequency Lists, or How to Release Statistics About 70 Million Passwords on Purpose. I'll start off with a few acknowledgments. The authors of this paper are Jeremiah Blocky from Microsoft Research, Anupam Datta from Carnegie Mellon University, and Joseph Bonneau from Stanford and EFF. This paper appeared in the annual Network and Distributed Systems Security Symposium, or NDSS for short, in 2016. Before I get too into the weeds of this paper, I think it would be beneficial to first start at a high level and discuss what some of these already encountered terms mean. So first I'll start by describing what is a password frequency list. A password frequency list, simply put, is an ordered list of the frequencies of all unique passwords for a given system. Importantly though, it is just the frequencies, not the passwords themselves. So given a data set of user-chosen passwords, a frequency list will reveal how often each unique password is chosen. In a list F, the most common password would be F sub 1, and the second most common password would be F sub 2, and so on. You can think of a list as a partition of n, where n is the number of users in a system. You may be thinking, okay, but why is this important? As mentioned in the paper, password frequency lists from empirical datasets have great value to security researchers who wish to understand the nature of an underlying password distribution so that they can accurately estimate security risks or evaluate various password defenses. For example, if we denote lambda sub beta as the sum of all partitions, which is an approximate upper bound on the number of accounts that an adversary could compromise with beta guesses per user, because a password frequency list allows us to compute lambda sub beta, then for every value of beta, this data can be useful for analyzing defenses against online attacks and offline attacks. An organization might use this data to help determine how much key stretching to perform on its authentication servers to mitigate damages in the event of an offline attack. Similarly, consider an organization which implements a K-strikes policy to protect users against online password attackers. A smaller value of K can decrease the usability of the authentication experience, while selecting a larger value of K can reduce security. The empirical data from password frequency lists could help organizations to make more informed decisions when considering the trade-off between security and usability. Currently, most password frequency lists come from data breaches, but this paper aims to find a way to accurately and securely put out a similar list. There is also a concept of adjacent data. Two datasets, X and Y, are said to be adjacent or neighbors if they differ in the data of just one individual. Mathematically speaking, two datasets are neighbors if their L1 norm, otherwise known as the Manhattan distance, is equal to 1. In this paper, that term is normalized by 1/2, and the authors claim that this leads to a more natural interpretation of the distance in a password context. In this case, if F represents the initial password frequency list, and F prime represents the frequency after a single user changes their password, then the distance between the two is guaranteed to be less than or equal to 1. This would make those two datasets neighbors. This is a key concept as it basically means the following. For any two datasets that differ on one individual's data, so imagine your data is taken out of a dataset, the distribution of results seen by an adversary should be about the same. How close the distributions are is given by a variable epsilon. So can we find a way to analyze data while guaranteeing that I cannot use that data to invade a user's privacy? The main theoretical concept behind this paper is something called differential privacy. Basically, differential privacy gives us a way to preserve privacy while using data in some analysis. It is a very broad and applicable concept held up by a few simple ideas. A dataset can have sensitive information about individuals, but how do we preserve those individuals' privacy if we want to analyze that data? That is the goal of differential privacy. We need some way or mechanism to maintain the integrity of the data without giving away information about specific individuals. Informally, a differentially private mechanism for releasing statistics about a dataset D ensures that an adversarial actor cannot use the output to make inferences about any individual in the dataset, except for inferences that the adversary would have been able to make without that individual's data from this dataset. Put another way, differential privacy is achieved by adding some small amounts of random noise according to the distribution of the underlying dataset to obscure the effects of individuals while ensuring significant statistical signal still comes through. This means that even if an adversary can interact with a system and run queries to obtain information about an individual, the information contained in that system should be essentially the same no matter if that individual is present in the dataset or not, and thus the adversary would not be able to learn anything new about the individual by interacting with this dataset. A core concept to differential privacy is something called a mechanism. A mechanism is simply an algorithm that introduces randomness into a dataset. There are several common mechanisms that exist in the field today, such as the Laplace mechanism, the Gaussian mechanism, or the exponential mechanism. These are basically just different formulas for how to generate draws when randomizing data. In this case, the authors start off using the exponential mechanism because they claim that the error rates from the Laplace and the Gaussian mechanisms are too high for this practical purpose. There is not enough time to dive too much into the theory here, but I think that the important takeaway is that we can use this mechanism to generate data that comes from the same distribution as the original dataset. So if we want to make a differentially private dataset, we will take the real data with some probability p, and with probability 1 minus p, we will generate fake data according to the same distribution, and that data is drawn from a mechanism. Epsilon is a very important term that refers to the privacy loss. We aim for small values of epsilon so as to preserve privacy. If epsilon becomes large, then you are preserving less and less privacy and not accomplishing the goal at hand. The other terms listed are really beyond the scope of this paper and presentation, but the main takeaway is that this equation generates draws that abide by the prior distribution of the original dataset. So you may be asking, okay, I kind of see what this is, but why not just anonymize any sensitive data or remove any sensitive data? Removing it means we can no longer work with it, which can be harmful for research endeavors. But anonymizing the data can also prove to be problematic. In the past, data from outside sources have been combined with data sets to essentially de-anonymize the information contained within a data set. This is called the linkage attack. You can link two or more data sets together to inform conclusions on the data present. Netflix has a famous example where they ran a contest for participants to try to beat their recommendation algorithm. Researchers were able to combine the data that Netflix provided, which included anonymized usernames, ratings, and other information, and then use an outside data set from IMDb to identify individual users and how they rated movies. In a more high-stakes example, the Massachusetts Group Insurance also ran into similar issues when they released anonymized healthcare data where adversarial actors were able to re-identify users based on zip codes, genders, and dates of birth to get medical histories. To wrap up the conversation on what is differential privacy, I will close with this specific type of differential privacy that we are working with when discussing this paper. This is a term called epsilon delta differential privacy. A mechanism is said to be epsilon delta differentially private if for all pairs of data X and Y differing in the data of one individual and all events S, then the probability of seeing event S in the data set, if the data set is X, is approximately the same as the probability of seeing event S when the data set is Y. They are at most e to the epsilon plus delta different. And again, the aim is for those values to be small to keep the chance of difference in the data sets very small. We typically aim for epsilon to be less than 1 and delta to be very near to 0. The smaller those values, the closer those terms are to equality, which means they are more privacy preserving. So how do you research passwords without compromising security? You can hash and salt them and use the resulting set of password frequencies to analyze passwords in some aspects, but how do you do so while ensuring no information leaks? Differential privacy is the answer to that. Now moving on to the crux of the paper, the authors present a novel approach to creating password frequency lists in a way that preserves the privacy of users. It provides the security guarantee that an adversary will not be able to use this perturbed frequency list to learn anything of significance about any individual user's password, even if the adversary already possesses a wealth of background knowledge about the users in the dataset. They go on to create a new mechanism based on the exponential mechanism that allows them to do this in an efficient manner and demonstrates that this works in practice on 2 real datasets. The goal of all of this is to provide new methods for securely researching passwords.
We talked a little bit about mechanisms, and specifically the exponential mechanism. So you may be asking yourself, why can't we just use that? If we combine our password dataset with the exponential mechanism, would the resulting set not be differentially private? And in fact, it would be differentially private. That would theoretically work perfectly fine. The issue comes from the practical implementation. As its name suggests, the exponential mechanism is an exponential operation in both time and space. This caveat makes it woefully inefficient and nearly completely intractable to use on a real dataset with 70 million individuals. For this reason, we cannot just use the exponential mechanism to make such a large dataset differentially private. To get over this, the authors came up with a variation of the exponential mechanism that is more efficient. To do so, they introduced a relaxation technique on the exponential mechanism. Current research suggests that it's hard to do better than an exponential time or space complexity operation in the general case. However, the authors did find a way to create a more efficient algorithm when working with integer partitions, such as what we see in a password frequency list. The standard exponential mechanism places a probability weight on each partition, but there are infinitely many partitions. In the proposed relaxation, the authors allow the mechanism to completely ignore partitions that are very far from the true distribution, thus making the technique more efficient.
So all of this is just to say that the authors present a new algorithm that is efficient and approximately samples from the exponential mechanism. We can say that since it approximately samples from the exponential mechanism, it approximately preserves privacy. This new algorithm is much more efficient than the exponential mechanism as it is approximately linear operation in both time and space. There is still the problem, though, of dealing with very large datasets. Even with this more efficient algorithm, when n is 70 million and epsilon is a small value such as 0.02, the space for the partitions would be nearly 200 terabytes. This calculation comes from the space complexity times 8 bytes, 8 bytes being the size of a double in C#, which is the language the authors used to implement this experiment. So we still have a big problem here. How do we break this down into something that we can actually compute? The authors discovered a way to represent the weights as a recursive function to which they then applied dynamic programming to efficiently compute them. The weights give a way to compute the probability of an individual component of the output frequency list, and the weights for a given partition can be computed by using the information about prior partitions. As a workaround, the authors mention that they build a dynamic programming table that stores only a small portion of the weights at any given time. They discovered that only a very small subset of the weights are relevant at any given time, so they prune the table to contain only those relevant values. On this part, however, they do not give much detail on exactly how the pruning occurs. So now we have a finite number of possible outcomes to draw from and an efficient way to compute the weights for those draws. The authors then go on to show proof that this new mechanism also preserves epsilon delta differential privacy. The proof for this is involved, but it can be intuitively summarized by the fact that the statistical distance between the distribution induced by the standard exponential mechanism and the distribution induced by the modified version is negligibly small. The standard exponential mechanism preserves pure epsilon differential privacy, and the delta term accounts for the negligibly small statistical distance between the two distributions. Because there is some distance between the two, we call this approximately differentially private. Pseudocode for the actual algorithms used in this experiment can be seen here. First, there is some pre-processing to calculate the weights of the partitions. This is shown in algorithm 2 in the middle. Then there is the actual frequency calculation shown in algorithm 1 on the left. And lastly, there are a few helper functions to find the upper and lower bounds for where to cut off the exponential mechanism discussed earlier. This is shown in algorithm 3 on the right. The authors then used a password dataset from a breach at RockU to generate a perturbed password frequency list. The dataset contained 31 million user password combinations and had approximately 14 million unique passwords. Interestingly, the most common password was shared between 300,000 users. They used a fixed delta value of 2 to the negative 100 and ran the data through their new relaxed exponential mechanism. They tested this with multiple values of epsilon, such as 8, 4, 2, 1, 0.5, and so on, all the way down to 0.002. Remember, the smaller the epsilon, the more privacy-preserving the outcome is. The first graph shows the average distance between the perturbed datasets and the original as epsilon changes. Smaller means more closely resembles the original. These results show tremendous privacy preservation even as the distance between the differentially private and the original dataset grows. Again, importantly, even as it grows, the results are still close. The second graph shows the number of entries in the dynamic programming table. While the values are still small enough that they can plausibly be contained in a realistic system, they do grow fast as epsilon changes. The authors mentioned that they achieved similar efficiency results by pre-computing most of the values and leaving some of the values to be computed on the fly. But they more importantly mentioned that while it has not been theoretically proven, or perhaps more importantly disproven, their empirical results show that they can achieve nearly identical results by further reducing the valid set of partition weights even further than their original proof suggested. The authors leave this as an open problem to solve in the future. All of this is to say that they created a privacy-preserving password frequency list from the RockU data breach. With Yahoo's permission, the authors used their differentially private algorithm to release password frequency statistics for approximately 70 million Yahoo passwords. This is currently thought to be the largest purposefully released password corpus in the world. The dataset includes frequency lists for many subsets of data for different groups of users. The authors claim that comparing statistics between different groups enabled many novel observations, such as stronger distribution of passwords chosen by older users or those with a payment mechanism stored on the system, meaning they found that users use stronger passwords when a credit card may be attached to that service. The image shown here shows the differences in computed statistics between frequency list that is not differentially private, which is the left, labeled original data, and that same list ran through the author's novel mechanism used to achieve differential privacy, which is on the right, labeled sanitized data. The differences are shown in italics and called out in red. In this image, n represents the total number of passwords observed. Lambda represents the size of the uniform distribution with equivalent resistance to guessing by an attacker with a budget of beta guesses, beta being the subscript of lambda. Big G represents the size of the uniform distribution with equivalent resistance to guessing by an attacker who makes enough guesses to achieve a minimum probability of success denoted as alpha, alpha being the subscript. Of the 52 distributions published, all but 3 showed virtually indistinguishable results from those of the original analysis. In all three of those groups where there were more noticeable differences, the group sizes were comparatively small, all less than 1 million users. Those three groups being Korean language users, users with more than 5 password resets, and users with more than 5 password changes. To sum up this paper, the authors presented an efficient mechanism for releasing perturbed password frequency lists. The novel algorithm guarantees minimal distortion while satisfying a strong security notion of approximate differential privacy. The evaluation on this data further demonstrates the practicality of the author's approach. At a high level, analysis on the perturbed data would have produced the same scientific conclusions and with nearly identical computed statistics as analysis on the raw data itself. Using these methods, data can be publicly released in a perturbed form rather than shared on a limited basis with trusted researchers. This is a great achievement for scientific progress and specifically research on password datasets, as well as other datasets that may contain personally identifiable information. I'll wrap up here by providing a link to the full paper, as well as a link to the actual password frequency list that was released as a result of this project. And lastly, if anybody is interested in learning more, here is a list of sources that I used while researching differential privacy, as this was my first time learning about it. It is a very interesting field that seems to have a lot of active research and some very meaningful real-world results. These concepts are widely used in real-world systems such as Windows OS, iOS and Safari, and all new systems from the US Census Bureau. Thank you.